Hi, and welcome to 14.1 Speed of Sound. So now we've talked about wave properties in general in Unit 13, and we're finally ready to talk about one of my favorite types of waves, sound waves. They're actually really cool the way they work. They're all just longitudinal waves. They're vibrations in a medium. Right now you're hearing the sound from your speakers, and the speaker's diaphragm is moving, and it's pushing the air molecules in your room, and the air molecules are moving back and forth like a longitudinal wave, which the waves travel, transferring energy to your eardrum, which vibrates in the same way that the diaphragm vibrates, but now it's on the receiving end. And that vibration in the diaphragm of your ear, the eardrum, gets transferred with these little bones that vibrate liquid in your inner ear, which that liquid vibrating vibrates little hairs or nerve endings in your inner ear. And we'll talk about resonance, and at a specific frequency, a specific type of nerve ending will vibrate, and that one particular nerve ending vibrating sends a signal to your brain saying, hey, I'm hearing this frequency right now. And that happens so fast and we take it for granted that that's what's actually happening, but sounds super cool. So first we'll talk about the speed of sound. So number one, a tuning fork vibrates at a frequency of 512 hertz. So it vibrates back and forth 512 times every second. That's what the frequency is, remember, when struck with a rubber hammer. The sound produced by the tuning fork will travel through the air as we said it, first of all, it's a longitudinal wave. Let's take a look at what that looks like again. So sound is a longitudinal wave. And if you see the little gray thing on the left side of the screen, that's like the tuning fork. That two little prongs that vibrate when you hit them. So the prongs are moving back and forth. Now, we said it was 512 hertz, so obviously it's moving back and forth much faster than this is. This is about 1 hertz, but the other one would be moving back and forth 512 times every second. Now, the little black molecules are air molecules, and see how this is pushing the air molecules, and then it's retracting back? That wave gets transferred through the medium. So it is a longitudinal wave in that way, where the molecules are going back and forth parallel to the velocity of the wave. So it's longitudinal. By the way, the speed of sound is determined by the medium. If you change the medium, then the speed will change. So let's look back at the question. So sound is definitely a longitudinal wave. Is it a longitudinal wave with air molecules vibrating parallel to the direction of the wave travel? Yes, that's the definition of longitudinal, not perpendicular. It should be parallel. Number two, which statement correctly describes one characteristic of a sound wave? A sound wave can travel through a vacuum. That is incorrect, because you need a medium to vibrate. If you don't have a medium there, if there's no air molecules, it's a vacuum, then how could you make a sound through that? It's like saying, oh, let me make a water wave, but there's no water. Can you make a water wave right now with no water in front of you? No, you need that medium. It's called a mechanical wave. So you need a medium. It can't travel through a vacuum. No. How about B? The amount of energy a sound wave transmits is directly related to the wave's amplitude. That is true. We're still talking about mechanical waves, so the greater the amplitude, that means you put more energy into the thing. It's not inversely related to the wave's frequency. The energy doesn't have to do with that. When we do electromagnetic waves, we'll see how frequency and energy are related. But for now, we're doing mechanical waves, sound, and the energy is related to the amplitude. Number three, as the density of a gas increases, the speed of the sound in the gas will. So what's happening here is the density of the gas is increasing. So let's say it's not very dense, and then you have a more dense gas where the molecules are closer together. Okay? Now this molecule has to travel all the way over here to the next molecule to transfer the energy. That's a long distance. This molecule only has to travel here, so it could transfer that energy in a quicker amount of time. So basically, the denser the material is, the faster the speed of sound will go. So this is just for gas. What about if it was a liquid? Those molecules are even closer together than the gas. So in liquids, sound travels faster than in gases. And in solids, they're even closer together. So sound actually travels fastest through solids because the molecules are so close together. They don't have to travel as great of a distance before they transfer the energy to the next molecule. So as the density increases, so does the sound, the speed of sound. Number 4, the sound wave produced by a trumpet has a frequency of 440 hertz. What is the distance between successive compressions in this sound wave as it travels through the air at standard temperature and pressure, STP? Hint, look in your reference table below to see how fast sound travels at STP. Right, so there's two different weird things about this. They give you a hint for one of them, so we're going to look to see the speed of sound at STP. We could look at our reference table. Let's do that now. So look at your reference table. Here we go, and it's right on the front page. It's a constant. The speed of sound in air at STP is 331 meters per second, or 3.31 times 10 to the 2 meters per second. So that's pretty fast. In 1 second, it could go 331 meters. That's fast, right? Now, what is STP? STP just stands for standard temperature and pressure. You might remember that from your chemistry class. So that's the first kind of weird thing. But look, now we have a given information. So that's the velocity of the wave. 3.31 will be fancy times 10 to the 2 meters per second. Okay. Now, and then you could write down the next thing. So I see a number here, so I'm definitely going to write that. 440 hertz. Hertz is the unit for frequency. They tell you it's the frequency. What's the other weird thing I was talking about? Well, if you look at the second sentence here, it says, what is the distance between successive compressions? This should sound familiar to some terminology that were in previous worksheets and previous videos. If this was a transverse wave, right? So let's just make a transverse wave. And for transverse wave, they use crests. The distance between successive crests is called the wavelength. So really, that's what they're asking for. It says, what is the distance between the successive, not crests, but compressions? So if you were to, let's say we plotted, do you remember what that looks like over here when this GIF is moving? All right, you had areas where they're close together and areas where the molecules are far apart. The close together areas are compressions. The far apart areas are called rarefactions, actually. And what you could do is plot the density. This is the density of the material at a certain position over time. And you'll have areas where it's like super dense, everything's close together, and then areas of rarefaction, so that'll be the trough. And then it's like the wave is passing through and it's compressing everything together again. So you could represent a longitudinal wave with what looks like a sine curve, a transverse wave, but really sound is not transverse, it is longitudinal. But you could plot the density. This is super dense, so it's high density. This is less dense than what it normally would be at equilibrium, so it's down here, right? It's not as dense. But still, the same thing holds true. The distance between compressions is still called the wavelength, and you could measure the wavelength like that. All right, so I'm going to clean this up a little bit, and let's see what we could do. So now that we know kind of what the given information is, that's part of the problem. Sure, we knew what the frequency was, but A, you had to look up the velocity, and B, you had to know they were actually asking for the wavelength. Well, we have the givens and the unknown. What equation are we going to use? We could still use the wave speed equation, V is equal to F lambda, to solve here. And we could plug in for the velocity and for the frequency and solve for the wavelength by dividing 331 divided by 440. And you get about 0.75 meters. So that's how long a wavelength is of a 440 hertz sound wave, which I think is like an A note is 440 notes. So if you're sounding an A on any kind of instrument, the sound wave that you're that you're making has compressions that are 0.75 meters apart. You could probably visualize what 3/4 of a meter stick is. So that's a like fair distance. If you could see the compressions, you could like make out what it is. It's not like it's a super tiny wavelength. So that's kind of cool to think about. A says a 512 hertz sound wave travels 100 meters to an observer through air at STP. So anytime you see like the capital STP thing in this unit, it's telling you some hidden information. Like we said before, the STP means the velocity of the wave. It's a sound wave. If it's a sound wave at STP, the velocity is 3.31 times 10 to the 2, or 331 meters per second. That's what the reference table tells us. Now, the frequency of the wave is 512 hertz. We know that. We also know it travels a distance of 100 meters. But what is this asking for? It says, what is the wavelength of the sound wave? Right now, for part A, we don't care how far it travels. 100 meters is about the size of a football field. So if this is our football field, wow, look at this great football field. Looks like 2 tuning forks. Okay, so let's say there's a trumpeter or maybe a drum is being banged over here, and then the sound wave travels all the way across. Do we care what that distance is if we're looking for the wavelength? What is the wavelength? Doesn't matter, right? It could have traveled super far, or maybe it only traveled a little bit. That's not going to change what the wavelength of that sound wave is, right? So right now, this information is not really necessary. We're not going to use it to solve for the wavelength because we're going to use the same equation, V is equal to F lambda. And we don't need to know, like, D, what the distance is for that. So let's figure that out. You plug in 331 for the velocity. This time, it's a higher pitched sound wave. The frequency is higher. 512 hertz, and we're looking for the wavelength. So 331 divided by 512, that's about 0.65 meters. So the higher frequency means that the wavelength is shorter if it's the same speed, because there's more waves per second passing by. So that means that the wavelength must be smaller, right? If there's more waves passing by at the same amount of time, then the wavelength is smaller. Now it says for B, it says how many seconds does it take for the sound wave to travel to the observer? So now we are looking at that football field. And we have a sound wave, and it's traveling with a velocity, and the wave is traveling 100 meters. That's the distance. So, and they're asking how many seconds does it take? So what's the time? So this is actually reminiscent of the very first equation that we did in this class. We know what the velocity is. We know what the distance that wave is traveling through, 100 meters. And we could figure out what the time is. We're going to do our good old friend, V is equal to D over T. So 331 times 10 to the 2. Oh, my bad. Ooh, were you like screaming at your screen? Mr. Nagel, you made a mistake. Don't send me any emails yet. I fixed it, okay? All right, I try to be fancy. 3.31 times 10 to the 2. 100 over T. Now, maybe you got mixed up on this. So anytime the T or the variable's in the denominator, it's easy to make a silly mistake. I recommend cross-multiplying first. And then now maybe you can see, oh, I have to divide this way. A lot of times people will they'll flip it by mistake. You actually do 100 divided by 3.31 times 10 to the 2 because the T was in the denominator there. So you should get 0.3 seconds. Wait a second, what? It only takes 0.3, not even a second, not even really a third of a second to go all the way across a football field, 100 meters or 100 yards. Sound travels very fast. Can you run a whole football field in 0.3 seconds? Can you run a whole football field in even 1 second? No. If you could, I'll give you a football scholarship. How about that? I guarantee if you run a whole football field in 1 second, I will pay for you to go to college. Anyway, number 6. What is the wavelength of a 2.5 kilohertz sound wave traveling at 326 meters per second through air? So let's write down our stuff. We're getting a little fancy here. So they're asking for the wavelength. What is the wavelength? But look at that. That's the kilohertz. What is that? Well, hertz is frequency, right? But how do we write kilohertz? If you look at your reference table for the prefixes of power of 10, that's all the way over here. First page, kilo means times 10 to the third. So in kilohertz, if you just replace times 10 to the third and then go hertz, that's how you handle that. So you literally just write the number that they tell. Okay, 2.50, that's fine. Change kilo to times 10 to the third and then continue on, hertz. That's a kilohertz, a kilohertz. All right, so you could rewrite it like that. So that's what we're looking for there. If you didn't do the times 10 to the third on this one and you couldn't figure out why you got it wrong, that's probably why. And it's traveling at 326 meters per second through air. So the velocity is 326 meters per second. Okay, so that's a little bit slower than what we normally do for STP. Okay, so something's making that velocity go slower. That's fine. The medium is different. Maybe it's not at STP, the air. So they're looking for the wavelength. We're going to do V is equal to F lambda. Plug in 326 over here. Make sure you're doing 2.5 times 10 to the third because it's a kilohertz. 2.5 kilohertz times the wavelength. And when you're dividing, make sure you're either using the parentheses or you're using the E button, the capital E button. And you should get 0.13 meters. So it's a higher frequency, and the waves are even closer together than those two other ones that we did up here, number 4 and 5. The higher the frequency, in general, the closer the wavelength is, given the same velocity. Now, the velocity was a little bit different, but not that much different. All right, here we go, number 7. An outdoor physics demonstration, a delay of 0.5 seconds was observed between the time sound waves left a loudspeaker and the time these sound waves reached a student through the air. So it's kind of like part B of this question, where the sound wave has to travel a distance before it's observed by the person. So in this case, it was a 0.5 second delay. So the speaker makes the sound. 0.5 seconds later, the wave finally has made it over to the student. So same situation. All right. So the time that it takes to travel is 0.5 seconds. It says if the air is at STP, anytime you see the capital STP, right, 3.31 times 10 to the 2 meters per second. Now that's only for sound waves. If it's different for light. Light travels much faster. At STP, it doesn't matter. Light is always going to be faster than sound. If the air is at STP, how far was the student from? So they're looking for now the distance, not necessarily, it's not the wavelength, it's the distance, kind of similar to part B of that question. So very different from the wavelength. They're looking for the distance. So we'll do the same process again, but now different things. So V is equal to D over T. It's STP, so that means 331 times 10 to the 2 is the velocity. They're looking for the distance, and now the time is on the bottom, which makes it easier. You just divide that by 2. You multiply by 0.5. And you get 165.5 meters. Oh, that's a weird-looking M. Okay, number 8. I think this is the last one, and this is one of my favorite ones because it is sound waves, and you might not have thought of sound waves like this before, but now there's sound waves traveling through water. So it says a stationary research ship uses sonar. Have you ever seen that on like TV shows or movies before, like the little sonar screen where it's like beep, beep? It's like the same thing, right? So a stationary research ship uses sonar to send a 1.18 times 10 to the third hertz sound wave down through the ocean water. So here's the scenario. You have some water, and then underneath the water is the ocean floor, and on top of the water is our research vessel. It's a boat. Maybe it's a sailboat. I don't know, but let's make it look like a boat. Now it sends sound down. The sound goes down and it echoes off, it reflects off the surface and it comes back up like this. And then there's a detector, that's part of the sonar device, and it detects the sound wave a certain amount of time after it's sent out. So it literally travels down here and then it travels back up. And it doesn't happen instantaneously. There's a certain delay that happens because it has to travel a certain distance and it could only go so fast. So let's read the rest of the problem. It says, the reflected sound wave from the flat ocean bottom 324 meters below the ship. So now we know this distance is 324 meters. And it is detected 0.425 seconds after it was sent from the ship. So it goes down and up in a total time of 0.425 seconds. So let me ask you this. Did it take 0.425 seconds to travel 324 meters? Or does it travel double that? It goes 324 meters down and 324 meters up in 0.425 seconds. So that's what I wrote, T total. And this is like D, almost like D half, if we think of it that way. D total would be 324 times 2 because you have to come up this way for the total time. You could also divide the total time in 2 and say, okay, I traveled this far down in half the time, 0.2125 seconds. Okay, so however you want to do it. It says calculate the speed of the sound in the ocean water. So that's a little bit confusing of a setup. You had to be able to visualize what's going on, and now I could do it 2 different ways to calculate the speed of sound. I'm definitely going to do V is equal to D over T, but I have to pick, do I want to use 324 meters, or do I want to use the 0.425 seconds, those 2 numbers that I gave us? I can't use them both because, as I said, it takes 0.425 seconds for it to go down and then back up. So if I wanted to use 0.425, I'd have to use 648, the total distance. Okay, the total distance, 648. You could also just say, okay, I want to use the 324 that they gave me, but I have to divide this time in 2. I know I'm being a little repetitive here, but it's confusing, right? And I'm not here with you. I'm not like right there with you. So I want to make sure you understand what's going on. Anyway, I typically like to use the total time because why not? It doesn't really matter. 0.425 seconds. One way is not necessarily better than the other. They're just different, and that's totally fine. I'm going to do 324 meters times 2. So D is equal to 648 meters. And now we could finally calculate what's the velocity. Okay. So V is equal to 648 divided by the total time for the there and back. Okay. So that's going to be equal to 1,525 meters per second. We're talking about a sound wave going 1,525 meters per second, whereas in air at STP it only goes 331. It's much faster through water. Like we said, that's because the molecules are closer together. They don't have to travel as far in order to transfer the energy. So they're able to more rapidly transfer that energy because the molecules are closer together. B, calculate the wavelength of the sound wave in the ocean water. So you had to do part A first to find the velocity. You need to know this. And if you rounded it differently, then you might get a slightly different answer, but it's going to be around the same, so it's totally fine. Meters per second. And you also had to know the hertz. So now you use that first piece of info that they gave you. You didn't need it for the previous part. which was also maybe a little confusing. Maybe you solved for the wavelength. No, in part A, you got to do the wavelength over here. And you had to find the velocity first. This is a good question. V is equal to F. Lambda, you plug in. Now that we know the velocity, and we're using this, now we could solve for the wavelength. So lambda is equal to about 1.3 meters. Now, make sure you're plugging this in your calculator with parentheses, or you're using the E button. Okay. Letter C says determine the period. Oh, this is a throwback now. Determine the period of the sound wave in the ocean water. For letter C, you didn't need to do parts A or B because they told you what the frequency was. And if you remember, the period and the frequency are inversely related. So you just do T is equal to 1 over F. T is equal to 1 over 1.18 times 10 to the third. And just a quick review, what does the period actually mean? This will tell us how many seconds it takes for one wave to pass through. Now, since the wave is traveling so fast, I'm going to assume it's going to take a very short amount of time for one wave to pass by us. So you do 1 over the frequency, and you get about 8.5 times 10 to the negative 4. What are the units for period? It's the period of time it takes for one wave to pass by. So it's time still, it's seconds. That's a very small amount of seconds. 0.123485 seconds. Pretty fast. All right, so that's kind of like waves, sound waves. That's all I got for you today. I hope you're all doing very well. Have a great day.